So in this presentation, I'm going to present the work mainly by Cynthia Kumar for a master's degree on analyzing a low bitrate audio codec. In particular, it's called Codec2 on an FPGA. So the goal of this work, as I just said, is to implement Rose, who designed the original Codec2, which is a low bit compression algorithm. It's a lossy compression algorithm that is meant for voice. So the goal is to look at how expensive it is on an FPGA. So we're going to analyze it with respect to area, speed, and power. And our comparison point is going to be a microcontroller, microprocessor, the Raspberry Pi with the ARM processor on it. So why would we even consider looking at the FPGA? Well, one thing we wanted to do is open source the HDL design for the Codec2. And then as a comparison point, just to see what's viable in the Internet of Things space. We want to see how effective it is in the hardware implementation. So that's why we're looking at the FPGA, and we have the potential for programmable hardware that could be optimized further. So our approach, we take the original C code for the Codec2. I'll talk a little bit more about what that is, and then we convert that into Verilog HDL implementation. So the main steps are we implement the C code as finite state machines from a control perspective with no optimization. Optimization in terms of parallelization, which is possible if you wanted to further optimize our original code base. We also, in this approach, had to determine the number representation. So in C, we have reals. We're moving into what's called fixed point. So that's the other step. And then once we have that fixed point representation of the numbers, we do need to implement some functionality for different operations using either existing intellectual property, whether that be through open cores or what's available in the Intel IP, or we make our own internal design for the operation. And then in the end, we evaluate area, speed, and power for the implementation on the FPGA versus the Raspberry Pi. So just so you understand the full digital voice radio system, where the blue boxes have the Codec2, you have a microphone, we do A to D conversion, then it gets compressed, then sent over, some sort of radio, modulated, demodulated, comes back in, and then the codec decoder recovers the signal, and then we can play that sound on a speaker. So that's the pathway. The base system, we can imagine that a Raspberry Pi, both shown on the top and the bottom, replacing those blue squares, is the device that does the encoding as well as the decoding. And other aspects of the radio could be put on those, but that's not the goal of this work. And so the key idea we're asking is, what if the encoder of the Codec2 is implemented in hardware? What costs does it have? So that's the goal of our system. So let's take a look at the encoder. So this is a block diagram of the encoder from Rose implementation. And you can see that from the speech samples, we convert various aspects of it into what we would call a frame. And that frame has so many bits in it as represented as the outputs of each of the boxes. So we want to implement each one of these boxes. Now that's a block diagram version of this. Basically, we're going to take this C code, which implements this, and is an open source available code with no rights. And we need to convert it into some sort of control algorithm. So that's basically our finite state machine. Don't worry too much about this, but this basically steps through all of the process. And then, so that's the control of the device. The next question is, which cores or operations do we need to implement? And this just shows, so in column 1, you see the source. So Open Cores is an online repository hosted by the Open Cores group. And we took their add and their multiply for fixed point and used those cores. We built a number of custom implementations of various operations, and you can see those in the first column with the label custom built. So division, greater than, floating point or fixed point, logarithm, cosine, sine, modulus, and square root. And then the last one that we used from the Cortis IP or Intel IP is the fast Fourier transform. So had to implement and test all these different functionalities. And then from there, we could implement each of the blocks. So here's an area estimation of each of the blocks. And what you can see is each of the boxes is also represented in the first column under encoder block, sometimes in a short form. So for example, the Fourier transform is the FFT, which is the second row in the table. And then for each of the implementations, we report how many logic elements it used, how many memory bits are used, and how many multipliers or DSP blocks, as they would be called on the FPGA, are used. You can look in the paper for more details on the area breakdown, because some of these blocks are broken up into smaller subsections, but this is just a good representation of how much area it costs to implement something. Overall, we're using the Cyclone 4 FPGA. It's a very specific FPGA available on the DE2-115 prototyping board. And what we're showing here is in the first column, that's the type of structure. So the FPGA structure that's available, and then available are how many are available on that specific FPGA. And then for our implementation, how many we use. So that's the third column. And then finally, what is the utilization? And so the most interesting thing from this table to note is that our implementation used 100% of the 9-bit DSPs, all the multipliers basically. And that's sort of the limiting factor in the implementation of our algorithm so far is we can't replicate these without more DSP blocks. So it's a very DSP heavy implementation. So that's the area perspective. Also with our implementation, there's a question of how good is it? So what we show here, these are the two designs. So on the top is the one with the FPGA. So with the FPGA, this is after taking it through the process and going to the ARM decoding phase. This is what we hear after this process. So I'll play that again. It's a little bit hard because there is some, it's not as good as the other compression. And then if we hear what the ARM processor is, which is an implementation with no errors because of the bit representations we hear. And again. So back to the one, so we can hear that it's worse, but it's still pretty good. So our quality is okay. We've lost a little bit. So we roughly have 6.55 bits per frame that are errors. And that most of the reason for that is that the number representation that we use. So the quality results are good enough. The area, we can see how much of the FPGA is used. And now the key question overall is, what is the speed and power comparison? So in this last table, we show that. So on the top is the Raspberry Pi is the encoder versus the second or the third column, which is the FPGA is the encoder. We show you the clock speed. So the Cyclone 4 on the DE2-115 is only clocked at 50 megahertz, so significantly slower clock rate. And then the runtime, so the time to process a 3-second sample. So the FPGA implementation is significantly slower. Now, the number of clocks it takes to process that 3-second sample, the FPGA doesn't use as many, but because it's clocked so much slower, that's why we get the disadvantage in terms of processing speed. But with higher clock speeds, we can start seeing that it becomes possible to start matching what the Raspberry Pi does. This can be implemented either through phase lock loops that are available on the FPGA, or a more modern FPGA could be used. And then finally, in the last column, we look at the energy. Again, the FPGA loses in energy to process the 3-second sample, but it's not as far off as in the time comparison. And you can very easily imagine that with a little bit of improvement in terms of parallelization, the energy costs would go down and it would be a significantly better implementation on the FPGA. So we're very close in a number of spaces. But again, our overall goal was we wanted to make an open source hardware implementation of the Codec2 encoder, provide the website link. Cynthia's GitHub portfolio is available there. And then we did our comparison. The FPGA implementation on the node we chose, the Cyclone 4 available in the D2115, does not perform as well, but we can start to see that there's potential. And the other key idea that comes out of this is, at least from our implementation, the limiter is the number of multipliers. And that's a factor in what types of optimizations could be done in further. Thank you.